Alright, so in this video I'm going to take a look at the June 2010 Unit 4 Section B. Let's make a start. So I want us to state the Newton's law of gravitation. So what the first thing is, the Newton's law of gravitation talks about the force between two point mass. The force between 2 point masses. So this is one of the assumptions in it, that the point masses is directly proportional to the product of the masses, and it's also it's inversely proportional to the square of the distance between them. So that's what Newton's law of gravitation is, and those are the two key points there. Okay, so Cavendish investigated it by measuring the force between uniform spheres. The radius of the sphere, large sphere, was 100 millimeters, and the small sphere is 25 millimeters. Mass of the small sphere is 0.74. Show that the mass of the larger sphere was about 47. And density of lead is this much. So the key thing here would be to work out the volume, which would be 4/3 pi r cubed. So let me grab a calculator. So let's calculate that. So we've got 100 millimeters times 100 times 10 to the minus 3. We'll cube that, times by pi, times by 4 divided by 3, gives you 4.18, blah, 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 blah. We want to, so hang on, let's write that down. Times 10 to the minus 3. So the mass is the density times V. So we're going to times that by 11.3 times 10 to the power of 3, which comes out at 47.3 ... which is going to be approximately 47 kilograms, giving it to two significant figures, which you would. And it wants you to calculate the gravitational force between the spheres when their surfaces are in contact. So the distance between their centers is going to be 100 plus 25 times 10 to the minus 3, or what's that? 1.25 times 10 to the minus 1 is the distance between their centers. So the force, we're going to go use, so it's going to be 6.67 times 10 to the minus 11 times by 0.74 times by 47.3 ... divided by effectively 0.125 squared. So let's calculate that to start with. So 100 times 10 to the minus 3, should have kept my answer, cubed, times by pi, times by 4 divided by 3. Do that times by 11.3 times 10 to the 3. Okay, so we've got the mass 47.333, blah, blah, blah. Times that by 0.74, times that by 6.67, times 10 to the power minus 11, divided by 0.125 squared, and that gives you a force of 1.495 ... times 10 to the minus 7. So that's just going to be, to two significant figures, 1.5 times 10 to the minus 7 newtons there. Alright, let's move on to the next one. Modifications such as increasing the size of each sphere to produce a greater force between them were considered in order to improve the accuracy of Cavendish's experiment. Describe and explain the effect on the calculations in Part B of doubling the radius of both spheres. So the first thing is the mass of them is proportional to the radius cubed, So timesing timesing r by 2 implies you're timesing the mass by 8 because it's 2 cubed. And the distance is proportional to the distance squared, so times 2r means that distance is times by 4. So let's think, so if we're gmm over r squared, so effectively what we've done is we've multiplied the top line by 8 and by 8, so by 64, and we've multiplied the bottom line by 4. So the force has in the end been multiplied by 16, so it's going to be 6 times greater. So it's about working out what happens to each of the properties. So each of the masses would be times by 8 because it's r cubed, but the distance between them is just proportional to the distance squared. So then you'd end up with 8 times 8, so times 64 on the top line, and times by 4 on the bottom line overall, giving you a net change of 16. Right, let's move on to question 2. Okay, so we've got a charged sphere, and we've initially got it uncharged. So it's going to move vertically upwards, so it comes to rest at a change in length of 18 millimeters. So first thing we want is the direction of the field. So we can see that the charged sphere is negative, so essentially that means if it's moving upwards that the top plate is going to be positive if it's going to eventually move upwards. So it looks essentially like that, which means the field is going to be going like this. So essentially the field is going to go downwards in order for it to be attracted upwards. Okay, the spring constant of the glass spring is 0.24 newtons per meter. Show that the force exerted on the sphere by the electric field is 4.3 times 10 to the minus 3. So F equals K delta L, which is 0.24 times by 18 times 10 to the minus 3. Let's calculate that. So 0.24 times 18 times 10 to the minus 3 is 4.32 times 10 to the minus 3, which is approximately 4.3 times 10 to the minus 3 newtons. Okay, so that's that one. Potential difference applied across the plates is 5 kilovolts. The charge in the sphere is minus 4.1 times 10 to the minus 8 coulombs. Determine the plate separation. So the force acting on it is going to be the field strength multiplied by the charge, and it's a uniform field, so we can put that as V over D times by Q. So that's the force. Now we want to get D, so D is going to be VQ over F. So we've just calculated the force, so we've got 5,000 times by minus 4.1 times 10 to the minus 8 divided by the force, which was minus 4.32 times 10 to the minus 3. I think so. Let's calculate that. So 5,000 times 4.1 times 10 to the power of minus 8 divided by 4.32 times 10 to the power of minus 3. And then that gives 0.0474 which is going to be 0.047 to two significant figures there. The switch is now moved to position Y. I'm going to get the diagram back up so I can look at this and the diagram at the same time. Okay, switch is now moved to position Y. Okay. So don't explain the effect on this. The effect of this on the electric field strength. Okay, so essentially it's disconnected from the circuit. So the field strength, or E, becomes 0 because it's no longer connected to the potential difference that's creating the electric field. So potential difference becomes 0. So what happens is that not the field charge so the charge flows from the negative plate to the electrons built up to the positive. So that's what happens. So we're now on the explaining part. So the charge flows from that. Therefore, the PD reduces to 0. E equals V over D. So therefore, E reduces to 0. Sorry for the bad handwriting there, so let's summarize that. So what happens is the field strength becomes 0. So the reason is the charge flows from the negative to the positive, so it discharges. So as it discharges, Q reduces, so PD reduces to 0, and because field strength and potential difference are directly proportional to each other, this means the field strength reduces to 0. Okay, with reference to the forces acting on the sphere, explain why it starts to move with simple harmonic motion. So the key thing here is initially the weight force acts to extend the spring. So that's what essentially is going to kick these things off. So the resultant force reduces as the spring extends. So as the spring extends, it's going to be a force backwards towards the equilibrium position from it, and resultant force ends up being proportional to the displacement, because remember the extending force F equals kx, and which is a condition of SHM. So that's one of the key conditions to be in simple harmonic motion. Your force has to be proportional to your displacement and in the opposite direction also, and so that's what ends up happening. As you extend it, there's a force backwards acting against the motion there. Alright, so let's move on. Okay, so we've got collision of two probes. So one of them's being ejected and we're modelling it as an explosion. Okay, so we've got some data. Discuss how the principle of conservation of momentum and conservation of energy apply in this instance, and this is one of the assessed longer answer question. So the key thing is, no external force has acted. That's always your starting point here. You can't apply conservation of momentum if one has. No external force has acted. Therefore, the total initial momentum equals total final momentum. So that's essentially the law of conservation of momentum. Let's actually finish writing. And the reason we can assume that no external force has acted is because the gravitational force is negligible. So that those would be the external forces acting on them, but it's going to be so small that effectively that's not going to have, and therefore you get them exerting equal and opposite forces on each other, or internal forces. In terms of conservation of energy, so total energy is always conserved. You can't not conserve energy in this instance. So initially there is only kinetic energy because the probe is travelling at a certain velocity in this case, so it's already moving, but in the explosion some may be transferred to what will you do to heat or internal energy. So essentially energy, so things might heat up, or you might send some energy to the surroundings. So that's what you'd expect to happen in terms of conservation of energy. So the total kinetic energy might decrease or be an inelastic collision. So that's what I would talk about there in terms of answering this question. Calculate the magnitude of the velocity of the capsule immediately after the explosion. So the total momentum before would be 500 times 160, and afterwards it's going to be the mass of the probe times by the velocity plus the momentum of the remaining section. So 500 times 160 minus 350 times 240 divided by 150. Velocity is going to be minus, because we know a minus number, 26.6622. So that's going to be 27 meters per second. So that means it's going to be to the left, because we're saying right is positive in that calculation. Determine the total amount of energy given to the probe and capsule by the explosion. So we essentially need to work out the initial kinetic energy, half times 500 times 160 squared, 0.5 times 500 times 160 squared is 6.4 times 10 to the 123 joules. The final kinetic energy is half 150 times 27.3 squared plus 350 times by 240 squared. So what was that? 27 plus a third squared times 150 plus 350 times 240 squared divided by 2. You end up with 1.01 times 10 to the 1, 2, 3, 4, 5, 6, 7 joules. So the change in the kinetic energy, or the amount of energy given, is going to be the difference between those numbers. So let's subtract from this 6.4 times 10 to the power 6, which is going to be 3.7 times 10 to the 6 joules, which will be your final answer. Alright, let's move on. So, we're looking at a magnetic field. Alrighty, so what have we got here? When viewed from vertically above, the electron moves clockwise around the in a horizontal circle. Which one of the 6 directions shown on figure 3 is the magnetic field directed? So at the location is at the moment, the electron is moving in the minus y, which means the positive charge is moving in the plus y direction. So let's put the motion that way. And then, so the force is going to be towards the center, which must mean the field is downward, so in the minus z direction. So we're using Fleming's left-hand law. So we've got the field going in the plus y direction, the force is going in the minus x direction, so then your field must be going in the minus z direction, which you will see on your fingers. Explain why the electron is accelerating even though it's travelling at constant speed. So velocity is a vector and direction is changing, therefore velocity is changing, so it is accelerating. So this is all because of the fact that velocity is a vector, direction is changing, so velocity is changing, therefore it's accelerating. Okay, so let's move on. By considering the centripetal force acting on the electron, show that its speed is 5.6 times 10 to the 6. So the centripetal force is from the magnetic field, so that's going to be BQV, and that's going to be equal to mv squared over r. So that's cancelling it, so essentially we're going to get V is BQR over m. So that's going to be, our field strength is 0.43 times 10 to the minus 3. It's an electron, so that's 1.6 times 10 to the minus 19, times by the radius. The radius in this question is 74 times 10 to, what power is it, minus 3. Again, this is all in the data. And we're going to divide that by the mass of an electron, which is 9.11 times 10 to the minus 31. Alright, so that's 0.43 times 10 to the power of minus 3 times 1.6 times 10 to the power of minus 19 times 74 times 10 to the power of minus 3. That's a lot of powers. Divided by 9.11 times 10 to the minus 31. And that comes out as 5.588 blah 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 times 10 to the 6. So that's going to be 5.58 times 10 to the 6, which is approximately 5.6 times 10 to the 6 meters per second, which is what we were looking for. Calculate the angular speed. So angular speed is the velocity divided by the radius. So that's what, 5.58 times 10 to the 6 divided by the radius, which was 74 times 10 to the minus 3, giving us a value of 74 times 10. 7.55 times 10 to the 7. 7, yeah. So that's going to be 7.6 times 10 to the 7 radians per second. Correct unit there. How many times does the electron travel around the circle in 1 minute? Okay, so the time is 60 seconds, so the radial distance it covers is 7.55 times 10 to the 7 times by 60, so that is 4.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9 radians. So the revolutions is the angular displacement divided by 2 pi, divided by 2, divided by pi, which comes out as 7.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 revolutions, or complete orbits, if you like. Alright, so let's move on to the next question. Okay, so we're looking at an electrical generator, so we're going to do some induction by the looks of it. So we've got a rectangular coil rotating, and it's at an angle, well, its normal is an angle theta to the field. Coil has 50 turns, an area of this value. We've got B, calculate the flux linkage when theta is 35 degrees. So flux linkage is BAN cos theta, so it's going to be B 2.8 times 10 to the minus 2 times 1.9 times 10 to the minus 3 times 50 times cosine of 35, 2.8 times 10 to the minus 2, it's 1.9 times 10 to the power minus 3 times 50 times cosine of 35, which is 2.178, so that's going to be 2.2 Weber turns times 10 to the minus 3, giving it 2 significant figures, because this information is all 2 significant figures. Okay, the coil is rotated at constant speed, causing an EMF to be induced. Sketch a graph on the outline axis to show how the induced EMF varies with angle during week 1 complete rotation. Okay, so when theta is 0, the flux linkage, the cosine of theta will be 1, so the flux linkage will be at a maximum, so therefore the EMF will be at 0, because where it's 90 degrees out of phase. So if the flux linkage is at a maximum, which it is when theta is 0, EMF will be 0. So we'll be starting at this point here. Flux linkage is 0 when theta equals 90, which means EMF will be at a maximum. So it's going to go up to here, going to go up to there, go down to here, and then up to there. So it's going to look a little bit like that. You could definitely argue that it goes the opposite way, so you could have sketched it like this. As long as you're going through the right kind of points, that would be fine as well. Either of those two graphs could be fine. Okay. Give the value of flux linkage for the coil at the positions where EMF has its largest value, or it's going to be 0, because that's where the gradient of the graph is maximized. So you can see here, because when cosine of 90 is 0, so the flux linkage will be 0. Explain when the magnitude of EMF is greatest at the values of theta shown in the diagram. So the induced EMF is proportional to the rate of change of flux linkage. At theta equals 90 or 270, the rate of change of flux is maximum as the coil is moving at that point. It's going to be parallel to the field. So that's when you're going to get maximum flux cutting, and the reason for that, because it is cutting flux lines perpendicularly, so it's moving across the most field lines per second, is what that's trying to say. So the first point is looking at essentially a mixture of Faraday and Lenz's law. So at these values of theta, your rate of change of flux is maximum because it's moving parallel to the field at that point, so it's cutting the most flux lines per second, so it's cutting perpendicularly across.